Hello viewers, I am BSSP Rajashekhar, Assistant Professor of Mathematics, Government Degree College for Women, Nalgonda. In today's video, let us discuss about the subspaces of finite dimensional spaces and solve some of the problems related to dimension of subspaces. Let us first quickly recap the definition of basis and dimension of a vector space, and we prove a statement that HBA is subspace of finite dimensional vector space V. Any linearly independent set in H can be expanded if necessary to a basis for H, and H is finite dimensional and dimension of H is less than or equal to V. We will prove this statement, and later we prove the basis theorem. Finally, we solve some of the problems on dimension. So let us quickly go through the required definitions, prerequisites for this class. So the first one is linearly independent set. An indexed set of vectors v1, v2, and so on vp in a vector space V is said to be linearly independent if the vector equation c1 v1 plus c2 v2 and so on cp vp is equal to O, the zero vector, has only the trivial solution, zero solution. That is, C1 is equal to 0, C2 is equal to 0, and so on, Cp is equal to 0. If this set has no other solution except zero solution, then we can say that the set is linearly independent. Similarly, if the set V1, V2, and so on Vp is said to be linearly dependent if the relation C1, V1 plus C2, V2, and so on Cp, Vp is equal to 0 has non-trivial solution. That is a solution other than zero solution. That is, if there are some weights or scalars C1, C2, and so on Cp, not all zero. Not all zero. That is, at least one must be not equal to 0, such that the relation C1 V1 plus C2 V2 plus so on plus Cp Vp is equal to O holds. So if we can find a non-zero solution, then we can say that the set is linearly dependent. And if we can't find a non-zero solution for this relation, then we can say that the vectors involved in this equation are linearly independent. So basis, let H be a subspace of a vector space V, and extended set of vectors B is equal to set of P1, P2, and so on Vp in a vector space V is a basis for H if two conditions. First one is B is linearly independent set, and second one is B spans H. That is, the subspace spanned by B coincides with H. If these two conditions are satisfied, then we can say that B is a basis for the vector, basis for the subspace H. If we can find a set, linearly independent set, that can span the entire vector space V, then we can say that that set is the basis for vector space V. So to find a basis for a subspace or vector space, we need to find a linearly independent set, and that should span the set subspace for which we are searching for a basis. And we have seen these statements in the previous classes. If a vector space V has a basis B is equal to P1, B2, and so on Pn, then any set in V containing more than n vectors must be linearly dependent. So if a basis has n elements, then any set with more than n elements must be linearly dependent. That implies if a vector space V has a basis B with n elements, then each linearly independent set in V has not more than n vectors. So if V has a basis with 10 vectors, you can't have a 11 vector linearly independent set for that vector space. And this is one more statement which we have gone through. If a vector space V has a basis of n vectors, then every basis of V must consist of exactly n vectors. So the number of vectors in all the bases of a particular vector space is equal. And dimension, that equal number is denoted by dimension of a vector space when that number is finite. So if a basis for a vector space V is finite set, then V is said to be finite dimensional, and the number of vectors in a basis for V is the dimension of V. So the common number in all the bases of a vector space is called the dimension whenever that number is finite. And we denote it by dimension of V. This is the symbol for that. So this shows the number of vectors in the basis of vector space V. So dimension of V denote the number of vectors of a basis for the vector space V. We take the dimension of null space or zero vector space as 0. And if V is not spanned by a finite set, then V is said to be infinite dimensional. So these are the things which we have gone through in the previous classes. Now let us prove this statement. Let H be a subspace of a finite dimensional vector space V. Any linearly independent set in H can be expanded if necessary to a basis for H. Also, H is finite dimensional and dimension of H less than or equal to dimension of V. So in this theorem, we are going to prove that any linearly independent set in a subspace H of a vector space V can be expanded to the level of a basis, and H is also a finite dimensional vector space whenever V is finite dimensional, and dimension of H is always less than or equal to dimension of V, where H is a subspace of vector space V. So these are the things which we are going to prove now. If H is equal to null space, that is equal to the set of zero vector only, then by the definition of dimension of H is 0. For null space, dimension of null space is 0. So here H is our null space, then dimension of H is equal to 0. And we know that dimension of a vector space V is a number, is a natural number. The number of vectors in the basis of vector space V, so it is a natural number, so it is always greater than 0, greater than or equal to 0. It is 0 when V is also a null space. If V is not a null space, it is always greater than or equal to 0. So 0 less than or equal to dimension of V. It is clear in this case. So since it is 0, we can say that H is finite dimensional. So there is no problem in proving when H is a null space. Let us assume that H is not a null space. Otherwise, that is if H is not a null space, let S is equal to set of U1, U2 and so on UK be any linearly independent set in H. Let us take a linearly independent set in H. Let that be S. So I have taken some vectors U1, U2 and so on UK so that they are linearly independent. If S spans H, if the entire set H can be spanned by these vectors, that is every vector in H is a linear combination of these k vectors, then we can say that S spans H. If S spans H, then both the conditions of a basis are fulfilled. First one, S is linearly independent, and if S spans H, it can span H. So as both the conditions are satisfied, S is a basis for H. Otherwise, there is some UK plus 1 in H that is not in the spanning set of S. So if S is not linearly independent, it is linearly dependent. Here we are taking that if S does not span H. If S is not spanning H, that means that there is some vector in H which is not a linear combination of these vectors. So let that vector is UK plus 1. So if S does not span H, there is some UK plus 1 in H that is not a spanning set of S. Then U1, U2 and so on UK plus 1 is linearly independent because no vector in the set can be a linear combination of preceding vectors. Already we have that U1, U2 and UK is linearly independent. So no vector is a linear combination of preceding vectors. Now we have added one more vector UK plus 1 which is not a linear combination of the first k vectors, that is U1, U2 and so on UK. So the new set U1, U2 and so on UK and UK plus 1 is also linearly independent. So we can add new elements like this as long as the new set does not span the H. If this spans H, our search will end here. Our search of a basis will end here. If this is not spanning H, then there must be some vector, some other vector UK plus 2. We named it as UK plus 2 such that it is not a linear combination of these vectors. So I can add that UK plus 2. If that is spanning H, our search will end here. That will be our basis. Otherwise, there will be another vector which is not a linear combination of those UK plus 2 vectors. So I can add some more vector. So I can continue this process until we reach a spanning set for H. So as long as the new set does not span H, we can continue this process of expanding S to a larger independent set in H. So we can add one more element and more elements, one more at each step, so that at each step the set is linearly independent. But the number of vectors in this set cannot exceed dimension of V. Since any set in V containing more vectors than dimension of V must be linearly dependent. We have already seen this statement. So if dimension of V is given, then that is the number of vectors in a basis of that particular vector space. So we can't form a linearly independent set with more than dimension of V vectors. So our process will end at a particular stage before reaching dimension of V or while reaching dimension of V. We can't exceed dimension of V steps. So eventually expansion of S will span H, and hence it will be a basis for H, and dimension of H is always less than or equal to dimension of V. So our search will come to a conclusion before the number of vectors reaches dimension of V, or number of vectors is equal to dimension of V. So it can't exceed dimension of V. So at a particular stage we can find that the expanded set of S spans H. In that particular stage, both the conditions linearly independent, it is still linearly independent, so we are adding vectors so that the set is still remains linearly independent, and at a particular stage that will span the entire set H, so that will be the basis for H. But that process must end at a dimension of V or before reaching that number. So that must definitely, the dimension of H must be less than or equal to dimension of V. So that is the statement, and this is another theorem, the basis theorem. So it shows that let V be a p-dimensional vector space and p greater than or equal to 1. That means V is not a null space. Any linearly independent set of exactly p elements in V is automatically a basis for V. Any set of exactly p elements that spans V is automatically a basis for V. So for a basis we need two properties, linearly independence and the set can span the entire space. So out of these two conditions, one can be replaced with the other condition, that the number of vectors equal to some number which is the number of vectors in a basis. So when we know the dimension of a vector space, that is number of vectors in a basis of a vector space, out of these two conditions, linearly independence and spanning set, out of these two conditions one is enough. Second one will be replaced with the dimension. So if we have a set with equal number of vectors with the dimension of a vector space, then it is sufficient either to prove it as a linearly independent or to prove it as a spanning set for the V, to show that it is a basis for vector space. After this theorem, let us prove the statements first. So, a linearly independent set S with P elements can be extended to a basis for V. This is what we have seen in the earlier theorem. So, any independent set can be extended to form a basis for the vector space. But the basis must contain exactly P elements, since the dimension of V is P. So all the bases must have equal elements. Here dimension of V is P. So the extended basis from S should also contain P vectors. So since S is already having P elements, no other vector can be added to it to form a basis. If we add it, it will be more than the number of vectors in the basis, then it will be linearly dependent, so it will not be a basis. So it is linearly independent and it can be converted into a basis by adding some more vectors, but that number should not exceed P. It already contains P elements. So all these statements conclude that S must already be a basis for V. Otherwise, we will get a contradiction. If S is not a basis, then by our previous statement, we can extend it to form a basis. Definitely, a basis can be formed using that set, that linearly independent set. That is our previous statement. So, if one more vector is added, there will be P plus 1 vectors that will be linearly dependent. So, S must itself is a basis for V whenever S is linearly independent and it contains P elements where dimension of V is P. So this is the first part of the theorem. Now second part, now suppose that S has P elements and S spans V. Since V is non-zero, it is given in the statement that P is greater than or equal to 1. That is, P is not a null space. So V is non-zero. By spanning set theorem, a subset S dash of S is a basis of H. Whenever S spans the entire set, we can get a subset of S, and out of S, we can form a basis for this space by eliminating the vectors which are linear combination of other vectors. That is the spanning set theorem. So by spanning set theorem, a subset S dash of S is a basis of V. It may be yes, sometimes S dash may equal to S, of course. Since dimension of V is P, S dash must contain P vectors. So S dash is a basis. We can form a basis S dash out of S. But since it is a basis, it must also contain P vectors. So S has P vectors. You can eliminate some of the vectors which are linear combination of other vectors so as to form a basis. but it should also contain p vectors. That means S is the required S dash. So S itself is the basis. Hence S is equal to S dash. So S is the basis for, this is a basis for H. So in both the cases are proved now. So from this we can conclude that any set of exactly p elements that spans V, where dimension of V is equal to P, is a basis of V. So at least one of the property of linearly independence and spanning set is sufficient when the number of elements, number of vectors in a set is equal to the dimension of the vector space. So this is the basis theorem. The dimension of null A and column space A. So dimension of null space A is the number of free variables in the equation Ax is equal to O. So to find out null space A, we form an argument matrix A0, the null matrix. We reduce into reduced echelon form. We reduce that augment matrix into reduced echelon form. We will find free variables there. So number of free variables in the equation Ax is equal to O will be the dimension of null A. And similarly, the dimension of column space A is the number of pivot columns in A. Number of pivot columns in A. So once A is given, we can reduce it into echelon form. Then we can find the pivot columns. There. So number of pivot columns will be the dimension of column space A, and non-pivot columns will give you the free variables. So number of non-pivot columns in a matrix which is in echelon form will give you the dimension of null space. So let us do this problem. Find the dimensions of null space and column space of A, where A is equal to -3, 6, -1, 1, -7. In the first row, 1, -2, 2, 3, -1. In the second row, 2, -4, 5, 8, -4. In the third row. So it is a 3 by 5 matrix, 3 rows and 5 columns. So let us first name the columns. Let the first column is B1, second one is B2, third one is B3, fourth one is B4, and fifth one is B5. So these are the columns of the given matrix. So let us form an augment matrix AO. So to find null space, we need augment matrix AO. So the 0 entries are added in the last column to the matrix A. So this is the augment matrix AO. and now we need to reduce it into echelon form. So to get free variables, pivot columns, we need to reduce the matrix A into echelon form. So this is matrix AO. In this, we are making the columns, these entries as 0. Since it is already 1, I am using this one to make this 0. So R1 goes to R1 plus 3R2. So that minus 3 plus 3 is 0. 6 minus 6 is 0. Minus 1 plus 6 is 5. 1 plus 9 is 10. Minus 7 minus 3 is minus 10. And 0 plus 0 is 0. Second row is as it is. For the third row, we are going to do R3 goes to R3 minus 2R2. So 2 minus 2 is 0. Minus 4 minus of minus 4, that is minus 4 plus 4 is 0. 5 minus 4 is 1. 8 minus 6 is 2. Minus 4 minus of minus 2, that is plus 2, that is minus 2 and 0. So this is the reduced matrix. Of course, by operating, this is equivalent matrix to the AO, augment matrix AO, by performing elementary row operations. Now here I am interchanging R1 and R2. So I need pivot position here. So that's why I am interchanging these two. R1 and R2 are interchangeable. So here we can see 5, 10 and minus 10. I can divide it with 5. So that I can get this one. First row is same and third row is same. Second row is divided by 5. So I will get 1, 2, minus 2, 0. Now you can observe that third row and second row are equal. Both are equal. So for third row, I can get the third row from by reducing it from second row. That is R3 goes to R3 minus R2. Will give this matrix. In the third row, all the entries are zeros. So we can observe that now it is in echelon form. So echelon form is sufficient to find pivot columns, pivot positions, and non-pivot columns. So if you want to find null space A, basis for null space A or null space A, you need to convert it into reduced echelon. But if you want to just find out the dimension of null space A, echelon form is sufficient. So now this matrix is in echelon form. You can observe that this is a pivot position, one is a pivot position, and this one is another pivot position. So there are only two columns, two pivot columns, first column and third column. So B1 and B3 are pivot columns, and remaining B2, B4, B5 are non-pivot columns. So there are three non-pivot columns and two pivot columns. These three non-pivot columns, when converted into equations, will give us three free variables, x2, x4, x1. So there will be three free variables out of these five. So this is O. The remaining five columns are representing 5 unknowns. This is x1, x2, x3, x4, x5. So b2, b4, b5, these three are non-pivot columns. These three are related to the unknowns x2, x4, x5. So we'll get three variables. So hence, as there are three free variables, dimension of null space A is 3. And since there are two pivot columns, dimension of column space A is equal to 2. So we can find dimension of null space A and dimension of column space A by reducing the given matrix into echelon form. So this is one more problem. For the subspace, set of column matrix S minus 2t, S plus 2t, 3t. So it's a 3 by 1 column matrix such that S and T are real numbers. Find a basis and state the dimension. So we need to find a basis for this subspace and to find out its dimension. If we know the basis, then the number of vectors in the basis will give us the dimension of the subspace. So let us name it as H. Let H is equal to the given subspace. So now H can be written as H is equal to set of S times 1, 1, 0. So here we can observe that there are two variables S and T. Now this matrix can be written as S times, here S is 1 time, so 1 is in the first row. Here again S is 1 time, so 1 in the second row. There is no S in the third row, so it is 0. Plus T times minus 2 plus 2 and 3, minus 2, 2 and 3, such that ST belongs to R, the set of elements. So if you add these two, you will again get the given matrix. So the given matrix can be separated like this. Now, if I name these two column vectors as V1 and V2, that is my V1 is 1, 1, 0 and V2 is minus 2, 2, 3. Now H is in the form of SV1 plus TV2. Now H is a linear combination of V1 and V2. Where S and T are real numbers. So H is spanned by these two vectors. H is equal to spanning set of V1, V2. That is these two vectors. Then V1 is not equal to 0. You can observe that it is not a 0 vector. So it is not equal to 0. And V2 is not a multiple of V1. So you can't get V2 by multiplying any scalar with this V1. So V1 not equal to 0 and V2 is not a multiple of V1. So we can say that the set of V1, V2 is linearly independent and spans H. So it is linearly independent and spans H. Both the conditions of the basis are satisfied by the set V1, V2. So we can conclude that set of V1, V2 is a basis of H. So in a basis of H, there are only two vectors. So dimension of H is 2. Therefore, dimension of H is 2. So basis is v1 v2. v2 v1 v2 is nothing but these two vectors 1 1 0 and minus 2 2 3. So these two vectors form a basis for the subspace, given subspace, and as there are two vectors in the basis, the dimension of given subspace is 2. And this is one more problem. Find the dimension of the subspace H of R2 spanned by 1 minus 5 minus 2 10 minus 3 15. So three vectors are given. Given that H is equal to span of V1, V2, V3, where V1 is equal to 1 minus 5, V2 is equal to minus 2 10, and V3 is equal to minus 3 50. So we can observe that V2 is a multiple of V1. If you multiply minus 2 with V1, you will get V2. And if you multiply minus 3 with V1, you will get V3. So clearly V2 is equal to minus 2 V1 and V3 is equal to minus 3 V2. So V2 and V3 can be produced by using V1. That is V1, V2 and V3 are linear combination of V1. So by spanning set theorem, we can eliminate V2 and V3. The set by eliminating these two vectors can still span the entire set H. So H is equal to spanning set of V1, V2, V3. This is given in the statement. That is equal to spanning set of V1. It is by spanning set theorem. And V1 is not equal to 0. This is not a zero vector. A single vector is linearly independent whenever it is a non-zero vector. So V1 is linearly independent and it can span H. So both the properties of a basis are fulfilled by set V1. So singleton set of V1 alone can form a basis of H. Since there is only one vector in the basis of H, we can say that dimension of H is equal to 1. So though there are three vectors are given, so one vector is sufficient to form all the vectors which can be formed by using all the vectors. So dimension of H is 1. Let us look into one more problem. For the subspace set of 2A minus 4B minus 2A such that AB belongs to R, find a basis, state the dimension. So here H is the given subspace is named as H, and that H can be written as A times. So here there are two variables A and B. So this can be written as A times 2. Here it is 2A, that is A times 2. 0, there is no A. So 0 minus 2A, so minus 2. Plus B times 0 minus 4, 0. Such that AB are real numbers. So let us name this column vector as V1 and this is V2. Now H is in the form of AV1 plus BV2, where AB are scalars or real numbers here. So H is equal to span of V1, V2. But here you can observe that V1 is not a zero vector and V2 is not a multiple of V1. So you can't produce V2 by using V1. So these two are linearly independent and they can span entire H. So V1 not equal to 0, V2 is not multiple of V1, therefore V1, V2 is linearly independent and spans H. Therefore V1, V2 is a basis of H. So since there are only two vectors in the basis of H, we can conclude that the dimension of H is 2. So similarly, we can solve problems. Thank you for watching.